In today's session, we're going to learn how to express an arbitrary function in terms of a polynomial and an associated error term. To do that, we're going to need to reach back into our bag of tricks a bit, going back to first and second quarter calculus, and look at the Taylor series, or what might be called the Taylor theorem. The Taylor series was really derived from a more basic theorem called the mean value theorem. And so we're going to start with the mean value theorem and borrow some graphics from Wikipedia to help us visualize what it's trying to say. If I could draw your attention to this graph and look at this dotted blue line, which we're going to imagine to be an arbitrary function. It will be continuous, it'll be smooth in the sense that it will have as many derivatives as we like, and it will be bounded between a lower point A and an upper point B. Now, taking the lowest point of the function and connecting it with the upper point, we end up with a secant line, which is shown in orange. What the mean value theorem is saying is that the slope somewhere along that dotted curve must be the same as the slope of that secant line. Now, it's not too hard to see why. It is somewhat intuitive, because if this blue line is continuous, and if it starts heading up at a rate much faster than the secant line is going, then for it to be able to work its way back to the destination point, it's going to have to curve back around, and somewhere in there, the slope is going to have to match the secant and then become smaller as it approaches the endpoint. Or if it wants to wander some more, there may be another place where the slope of the function, meaning the slope of the tangent line to that function, must be the same as the secant line for the same reason. If it's coming down too fast, it will have to turn around to get back up to the end value. So somewhere in there, the slope must be the same. Now, it might happen more than once. As you can see on this picture, it happens twice. We don't mind that. As long as it happens once, we're going to get good advantage of that. So we will then write that verbal geometric description that I just made algebraically. By doing so, we will express the slope at a tangent line, which granted is at an unknown location, and equate it to the slope of the secant line. The slope of the secant line is the rise over the run. This is the height at the end point minus the height at the beginning point, so that's the rise, and b minus a is the run. So now I would like to rewrite this equation to have it look a bit more like a straight line. So we have an outcome variable which is equal to some intercept times a deviation times a slope. I'm going to copy this formula that we have right here onto the next page, so where we can use it. And I've put it right here in the middle of this line, f of a plus b minus a times f prime of zeta. I'm going to replace b with the variable x in both its locations, and I'm going to replace a with the constant x naught in both locations. Let's go ahead and write that back down again. So here's our formula. F of x is a function evaluated at constant x0 plus a linear term whose slope is a function of this unknown point zeta. This formula can be thought of as having a predictor portion and an error portion. The prediction portion in this case is pretty simple. It is a constant, f evaluated at x naught. The error function is proportional to the deviation from x0. Now that makes some sense because I could use this as an approximation of f provided that I didn't allow x to deviate very far from x0. That's what this error term is trying to tell me here, is that if I do, the error is going to get fairly large. It will have a proportionality constant which is unknown, and we're hoping that f prime doesn't get really big, causing this error to become huge. Now that approach, the approach we're looking at here, is the same approach we're going to use all quarter long in understanding how to predict things numerically and get a bound on how much error that the formula will produce. This particular formula isn't very good, though. It's pretty weak because trying to estimate a function as a constant is very crude. We're hoping we can do better than that. So let's give it a try. And we're going to go back to our mean value theorem again and see if we can't get more out of it than we already did. The way we'll do that is consider a new function g, which happens to be the derivative of f. Now, there's no reason I can't use the mean value theorem for g, just like I did for f, provided that that derivative exists and it has the same nice behavior that f did. So we will assume that, and we'll just copy down the mean value theorem as we had before, using g's as my target function. Well, I can write that out again just using f prime. Since I know that g of x equals f prime, let's just write it down as it actually is. And when we do that, we realize we have a second derivative appearing evaluated at zeta, because since g is equal to f prime, g prime must be equal to f double prime by the definition of a second derivative. Okay? The other thing to notice is that f prime of x0 is still a constant. Just like f of x0 is a constant, so is f prime of x0. So we have a constant here, and we still have a constant on the right. Zeta is a constant, so f double prime of zeta must be a constant as well. That's good news, because what I'm hoping to do is get a hold of f, and I'd like to integrate this whole function here. The integral of a derivative is easy. That integration is going to return f, plus a constant, but we're going to get f back. If I take a closer look at the right-hand side, since I already established f prime of x0 is a constant, I can factor it out of the integral. And all I have left is the integral of dx, or you could say the integral of 1 times dx. And I can do a similar thing with f double prime, factored out of the integral, and I end up with an integral of a very simple linear function. So both these integrals are simple. Let's just go ahead and do them. So this first integral becomes just f prime of 0 of x times x, because that integral is x. And on the other one, we just get an x minus x, or x minus x0 squared over 2, because that's the integral of x minus x0. And we better not forget the constant of integration that we've been accumulating along the way. One thing I'm not really happy about is that it's a function of x in one portion and x minus x0 in another. But that shouldn't bother me, realizing that this constant of integration is arbitrary, and I could borrow from it, and I would end up with, a different constant, but it's still arbitrary, and I could put that extra piece into this term here in order to make these two portions consistent. Now, this turns out to be very convenient, because I'd like to find out what that constant actually is. The way that I can do that is evaluate this form using x equal to x0. So literally plug x0 in everywhere you see an x. I can write then f of x0 is equal to that constant plus f prime of the deviation of x0 with itself, and f double prime again with the deviation of x0 with itself. Well, clearly all of this portion here has to be 0. I've just got 0 added onto this constant. And what I ended up with was k is equal to f of x0. Well, that's nice. Just plug f of x0 back into that again, and I end up with what we'll now call the second order Taylor expansion. We have now a linear predictor instead of a constant predictor, and we have a quadratic error term. Now, that error term is going to be a lot better than the one we had before if x is still close to x0. So if this number is significantly less than 1, when you square it, that term will get quite small, and then we get to divide it by 2. So very clearly, this predictor has improved. Well, could I go farther than that? Yes, I can, because I can now take this formula and make the same substitution I had before. G of x is f prime of x. Go through the same kind of process I did before and reintegrate the new formula. I'm not going to do all that here, but you can imagine that process happening again. And when that happens, you very nicely get the exact same formula you had out before. You even turn what was the error term into now part of the predictor, with one exception. Instead of an unknown zeta occurring right there, you end up with a known x0 value. So now we have a quadratic, which is our predictor. It will work much better than the linear term, or the linear expression would. And our error term becomes a cubic. Again, we'll require that x stays close to x0. Now when we take a small number and cube it, it really gets small. And we have by necessity a growing factorial that's developing in the denominator of this error term. That's good news too, because that will cause the error term to get smaller yet. The only wild card is what happens to this derivative, in this case third derivative of f, at x0. Well, if x and x0 are close and zeta is trapped between them, and if the functions aren't going crazy on you, then this ought to stay fairly tame. And what will drive the error term is the balance of that polynomial term. So that's all very good news. We can now write that down as a general formula. Here's what our error term looks like. It looks just like the last term, except evaluated at zeta and increased value of n by 1. Okay, f sub n, by the way, with a parentheses around it, means that you've taken the derivative n times. It gets kind of awkward to keep putting little apostrophes there. And of course, this means your function has to be well behaved and must continue to be well behaved as you're differentiating it. If it's not, the Taylor expansion doesn't work. So this is going to become the basis of much of what we do for the rest of a quarter. The key attribute here is that even though the error is approximate, since zeta is bounded, and if we choose functions that aren't really bizarre, then we can get upper bounds on our error by taking a worst case zeta. Here's our formula that we have, just nicely and convenient for you because you're going to get a chance to use it in the homework after the next session. And just a nice easy reference to what we just agreed on. So here we are at the end of the section. Next time we are going to pick it up here with the Taylor series, except we're going to do some applications. So we will look at some examples of use of the Taylor series on section 1.2b. We'll see you next time.